And welcome. I guess there is too many people who prefer the sunshine to the acoustics, which means that you are the chosen ones. Cool. So today, as usual, I would like to reflect back on what you've guys done last week as a matter of practical. So let's briefly look at that and actually repeat some of it just to be able to strike a discussion. Okay, so obviously I've seen all the groups as you were finishing up, but real thorough discussion I believe has not taken place yet, although there was a group that seemed to have taken it back home and continued. So there might have been intense discussions. But in any case, what I'll do now is rather small now, the resolution. Can you guys read that, yeah? So this will be today's. Let's check out last week's. So there were essentially two things that kind of supposed to be a bit new and, new tools in what you consider valuable among the other tools. So obviously just the basic measurement of the spectral response. You kind of expected that. You've probably seen it before the module. Now, what are the two things that we've done within REW that were hopefully enlightening?
The actual graphing out of it I found very helpful in sort of understanding. So I've seen these graphs before, but I didn't necessarily understand them in the same way that I do now, and the way that you do them at different frequencies and stuff.
Yeah.
And how sort of drastic some of the
yeah, the small movement. Yeah, exactly. Yeah.
And how much it does actually fluctuate.
You are the ideal student. But so that's exactly what we're after, kind of getting the feel for things. If once you do things yourself, you tend to remember them much better as well, right? So it's quite important. I will ask you, I still have only the title which says, please swap roles this and that. But I'm actually thinking what I'll do, maybe starting next week, is just select the software operators at random and kind of randomize the groups a bit, because you're probably going to get bored. Obviously you're, sticking to your best mates anyway. But you're likely to get bored, and kind of mixing up the groups is very valuable. But what is really important that everyone has a go at the software already in this, let's call it safe environment, at least safer than against the deadline. So, if you don't have laptops, if you're not bringing it normally, start doing that, and then one or the other week you should be doing the software bit, okay? The other bits are a bit more self-evident, I guess, placing things around and all of that. I was kind of considering, requesting, a summary of what you've done. But I don't want to really push you and make it there's so many things we have to do. But if there is a group which is kind of proactive, and there's a few groups like that, feel free to, conclude, finalize the graphs, the tables, kind of try to wrap it up if you like. And I'm very happy to reflect on that. Because if I reflect on that now, and not only after you've submitted, you get it, you will have an advantage in terms of having tried it, having had some feedback. In fact, as far as education goes, I think the feedback after after it's done is not as useful. So I would actually prefer to give you much more feedback before you submit, because experience shows that half of students don't even read the feedback that they're giving. They're just, through with it and gone with it, and that's it. So, that's the reason why I'm trying to, make it such that you are doing the things that will be the part of assessment already, and that you're already getting good feedback on what you're getting done. So assessment has been nodded at, so it will be part of today's class. I will talk you through that as well. So first part, discussed the previous week. Second part, assessment. Third part, this week's stuff. That's about it for today, probably. So the question remains, so what are the two crucially, supposedly new techniques that we've done last week? It's right there. So first thing is averaging. Okay, so as you've mentioned, correctly, right, you've noticed that the variability of measurements, even with small movements, is quite significant. Okay? So if you want to establish a measurement that tells you more than just that specific spot against that other specific spot, which is essentially what we're doing, then you want to move things around a bit. And if the distance is generally the same, then you average things, average these graphs, and then you can actually see what is common, right? Because it could be that there is a certain anomaly, let's say a certain peak, which is surprisingly large, but it's only in one of the 5 measurements around the same spot. In that case, you know that you've caught an anomaly that is very place specific. But if you want to consider a listening area, right, then you really don't want to confuse a very specific anomaly that is pertinent to only a single spot. You don't want to confuse that with the actual general characteristic of the listening spot. Right? So that's what we were really after when we were doing this. And I'm going to do something similar in a bit. Just measure around the same position a few things, and then we can try and do this together. Okay? So that would have been the crucial thing from this listening position or listening area estimation, is to figure out what is the trend, what is actually the case for the whole area, and what are the anomalies that don't hold for the whole area, but only specific spots. Okay, so that's averaging SPL responses. Okay, so that's your new tool. Try to remember it. You can always average things when you know that the anomalies can be very location specific. And the second thing that we've done is SPL alignment. Okay, and I'm taking them together just so they never get confused, hopefully. Right? So with the SPL alignment, what happened is that we had a measurement scenario whereby the distance was changing. Right? So if the microphone is in the same spot and I'm going to do something similar and I'm moving the speaker back and forth, then the absolute SPL is changing. So I don't really have a good basis of comparing the spectrum, right? So that's why I'm trying to take out the absolute SPL, so to speak, out of the measurement, which is this SPL aligning. So even if I have, dramatically different distances, I can compensate for the level difference. Okay? So those are the 2 main tools from last week, averaging and alignment in SPL. Okay? Cool. So let's do a bit of that. So what I have here, this is my office measurement. I'm going to remove that. This is the one that I've just done while you guys were talking a bit. And it was noisy. Actually, that thing up there is quite noisy anyway. So it is actually useful to potentially track the issues. Okay? So if I look, one of the best ways to track anomalies in measurement altogether is to look at the distortion figures. Okay? Now this one we don't really have a huge amount. Here the total harmonic distortion comes to 0.210%, which is not huge. Why? Why would I ever see an issue during the measurement, a car passing by, someone sneezing, whatever it is, in the distortion graph? Why do I expect to see it there?
There might be some frequency content that overlaps harmonically with the sleep.
Exactly. I mean, typically you would expect that the anomaly is not someone turning on a sine oscillator next door, right? So typically you expect the anomaly to be broadband, right? Now, if you look at the distortion characteristic, what does it actually tell you? It tells you, and we'll talk about this in more detail, that at a given frequency, let's take an example. Let's take frequency of 100 hertz. Okay? At this frequency of 100 hertz, these graphs down here are actually measuring the energy at 200, 300, 400, 500, and so on hertz. Right? So if there is no external disturbance, then obviously this will reflect the amount of distortion that comes typically from the speaker. Sound cards and microphones are much more linear than speakers, right? And obviously, rooms are linear. Okay, so you don't expect the room to add a harmonic to the input signal at all, right? So anything else but the distortion of the speaker would typically be an anomaly that was an external sound picked up by the microphone, right? If I sneeze, hashoo, right? It's a really broadband signal. So if I sneeze at any point while the sweep is running from low to high, if I sneeze when the thing was at 1 kilohertz, then this graph would give me a high anomaly at that stage. So actually, you could potentially say, even though the THD is kind of stable, you see that we have, which harmonic is that? Second, third, the brown. There is one of these harmonics, this one here, that actually has an unexpected peak just there. Okay, so it might as well be that this was caused due to extraneous sound. So let's see the same measurement again, and now I will make sure that I shut up at least. Okay, so this is my second measurement, and you see those peaks are gone. You see, I'm still looking at the distortion graph here. So this was the distortion graph a minute ago, and that peak is gone, and this peak is gone as well. Okay, so it is likely that those were indeed some sounds that someone, accidentally made while I was just running the measurement before the class. Okay, now let's see how these two graphs compare. So you probably know by now all SPL is the tab that allows me to view both SPL readings. Okay, so what can we say about this thing here? Well, they're nearly identical, but actually there is some difference, evidently. How much the difference is, well, I see here just above 1 dB. That's probably the largest difference so far. So it's not huge, but supposedly 1 dB is quite audible. Now, what can we say about this graph? First of all, you understand that this is not the room response. Yeah? How would you exactly specify what are we looking at? We're looking at the response, and I'm going to repeat this maybe every week because it's really important, of a given microphone, of a given speaker, of a given microphone position, of a given speaker position, 4 variables, plus the room. Okay? So that's really important to understand, the limitations of what we're doing here. Now, you may have, I've kind of spent some time talking a bit about the trade-off. What is the trade-off that we're looking at when we analyze spectra? The resolution trade-off between? Exactly, right? So what you've seen me do already once, and I probably won't repeat that bit, is that if I reduce the FFT size, or the window of analysis, what I get is more analyses per time frame, per second. So I get a higher time resolution, but I get a lower frequency resolution. Now, this is a fairly high frequency resolution plot. And this is actually the only one that truly allows you to appreciate the nulls. Okay? So big chapter, huge chapter, worth considering are the nulls. So what you see in the response there is troughs dropping down to 60 dB, but arguably they drop down to infinity, because rooms are such acoustic beasts that they have their nulls. right? So if I have these positions fixed, it is likely that there will be multiple frequencies at which you get exact cancellation. Okay, and this is the most problematic thing, really, and this is the thing you cannot fix with an equalizer. I mean, I should probably spend some time talking about other things that you can't fix with an equalizer. Is it a good time to do that? I mean, obviously you cannot fix bad mood. Unless you guys, I got a Neumann 310 in the post the other day. Buy it, sell everything you own. Get those speakers, they're just amazing. Never mind that. I have a null in the room anyway, but the speaker is just amazing. So what is it that we cannot fix with the equalizer? Other than the troughs, the nulls. It is the time response. Okay, so that's the thing that you kind of hopefully get a sense of and realize that it's a bit weird, but actually filtering, right, is a linear process, a time invariant linear process. But it can ring on, a filter can ring on. So no matter that we call it time invariant, and no matter that we always look at, plots describing filters which are snapshots in time, filters actually have behavior in time. They can ring on. And typically, filters ring on if they are narrow band. And these two things are tightly connected. So the narrower band of the filter, the longer it will ring for. And it's not just for band pass filters, it is also for low pass, high pass, in which case it's not the bandwidth, but it's the slope, exactly. So the sharper the slope of your filter, the longer the time response will be. And this is kind of inevitable, both in digital systems, analog systems, and acoustics. Through FFT, through orthogonal transforms, we can, help this issue. In fact, the brick wall filter is something you can only do through FFT. So actually cannot produce a filter, neither analog, neither digital, neither in acoustic space, that has an extremely steep slope. You can only do that if you do an analysis, fiddle with the data, and resynthesis, right? Which is not exactly a filter, but it can be done, right? So that's the thing to understand. So first of all, if I am, concerned with this, and I start pushing up, EQing up those frequencies where there is a null, right? What I will get is that the more I push it, the more it eats itself, right? This is the beast that feeds on itself. Right? So the more I give it, the more it will have to eat off itself, right? So you can't really push these frequencies with an EQ because the room eats them up, so to speak, right? So that's quite crucial. And then if I have a peaks are typically things that you can tackle with an EQ, but if I do that, what do I get? There could be phase anomalies. Phase anomalies are typically things we hear well with transients. There is much to say about phase anomalies. Speakers aren't perfect, not even nearly as far as that goes. And in fact, that's why you pay, multiple thousand quid if you do for a good speaker, because it has a very clean phase response. But what I'm getting at is that if I have a peak, right, it is likely to be a signal that spreads in time, right? The narrower the peak, the longer time it takes to ring out. So if I take an EQ and push that peak down, I still have the ringing. It's just a bit softer. Okay? So obviously there is something to say about, getting a flat spectral response from your system and so on and so forth. But beware that you're not fixing the problem, you're fixing part of the problem, let's put it that way. Okay? Any questions so far? Cool. So what I'll do then is I'll just gonna move this microphone a bit. So I'm gonna emulate the testing of a listening area. Okay, and one more. Cool, I'll settle with that. So what you see here then are 3 graphs, actually 4 graphs. 2 have been done at the same spot and 2 at a slightly different one. And what you can observe is that the nulls are actually fairly stable, at least some of them. Okay, so that kind of gives you, I mean, what was the variance of position here? Maybe 10, 15 centimeters. I didn't move it much. Now, remember that typically when we assess rooms, we are mostly concerned with bass. So it is useful to check out the bass frequency more than anything. So what you will see here is that, for example, this dip and 132 Hertz has actually been detected by all 4 measurements, right? Similarly, this one, the green didn't really catch it, but these are serious dips. So what do we do? How do we deal with these dips? We can't EQ them in, so to speak, right?
So you treat the room then?
You treat the room. But I have a dip, and how can I, because when I treat the room, I absorb sound, right? So,
Because it's, you're stopping the wave interacting with it.
exactly. Yeah, so I hope that was suddenly like, wait a minute, but I'm trying to treat a dip by absorbing even more. Error. But it's not an error, because indeed what you have is that energy is present in the room. But at the location of the microphone, it is canceling itself out. So if I reduce the energy in the room at that frequency, I will be helping the dip, right? Especially if I manage to do it such that, I find a nice spot for the bass trap, so to speak. Okay? So indeed, we can fix dips by treating the room. And you know that dips like this are caused by what? What is the cause of the dip?
Round face at this point in the speaker. Round point of the microphone.
Yes.
A null point at the point where the
Yeah, so what will determine the frequency of the null?
size of the room and the frequency.
Well, the size of the room, the position of the speaker, and the position of the microphone. But if we distill that, there is one thing that crucially determines the frequency of the null. We call it path difference, right? So that's the thing, because you have a path difference between a direct sound and a reflected sound. In fact, you could have the path difference between multiple reflected sounds. And that's the thing that happens if the sound recombines, so to speak, if there are multiple paths with a path difference, and at some point it's being summed, you will get these dips. Okay, so it is the path difference that does it. Cool. So first thing, average the responses. Okay, so that's what we've looked at yesterday. And here the question is, do we see anomalies that are pertinent to a given spot more so than to the listening area as a whole. What's your estimation? Well, not hugely. There is something going on around 100 hertz, which seems to be more location specific, right? Because you're essentially looking at how thick things are around the blue line. And as long as they're all neatly packed together, you know that those are the characteristics for the whole listening area, right? And there around 100 hertz, we have something which indicates that there is a large amount of difference at 100 hertz within the listening area. Okay? So in that sense, if you want to treat something, you probably focus on the things that are common and surely pertinent to the whole listening area. Let's look at how this maps out for higher frequencies. And there what you see is much more variability. Okay? So this is something you can conclude, and it kind of is self-evident, that at low frequencies, small differences in position aren't as crucial as they are at high frequencies. Okay? So at high frequencies, it all pretty much averages itself out, but you get a nice thick, band of essentially location-specific anomalies. Now, if you were to look at this graph, I mean, obviously this is not the control room setup anyway, what would you try to tackle? What would be your first call? Yeah, you really want to get rid of those nulls. This looks like a huge anomaly here at 300 hertz, right? So obviously, it's something of a visual thing. In all honesty, I probably wouldn't even plot a graph before I, introduce at least a few bass traps in the room. Anyway, and we will talk about absorption and placement of these due course. Okay, so that was one thing, and I don't think I'm going to run the second task from last week, just because I don't want to run out of time. But it's a similar thing in the sense that I have multiple measurements. In this case, I would be looking at distance of the speaker to the wall. And the thing that you should notice is there should be dips and peaks that move with the distance. This is slightly more complex because essentially if there is a very strong null and I move the position a little bit, what you get is that the amplitude is changing, but the frequency isn't, right? So those are the nulls that are really pertinent to the room. If I have a dip which is not pertinent to the room, but to the positioning of things, then repositioning will actually move the notch. Okay, so that's the interesting thing to check. If you can identify the notches that go only up and down with repositioning, and identify the notches that move in frequency with repositioning. All right? Cool. So obviously that's a bit advanced, and essentially you see, the basics are there. You guys are getting the basics already. Obviously I'm trying to push to, deeper understanding of stuff, but actually this is way beyond first class already, probably. And if I read a bit of this in your assessment, which I'm about to talk about now, then I'll be very happy and be like, all right, they've really got it. Okay, so let's briefly look at the assessment. I won't spend too much time with that, especially if I find it quickly. I've tried to be organized these days, or shall I trust the search engine? Here we go, assessment brief 2425. Okay, I will upload it very soon today. I didn't have the official signature yet, I just had the nod. But in essence, it's a fairly straightforward thing. There is a single point of assessment. Deadline is 27th of January. Okay, that's why we want you to submit this. You have this late submission window, that's all good. You probably know that the last lecture, I believe, is 19th of December. Okay? And in this period, actually, I will be back, I believe it's going to be 16th of January. So there should be good 10 days where I will be available to help you out. Okay? The thing to note is that the real gear is limited. You probably know that we have 5 sets. Actually, I think we have about 7 measurement microphones. Maybe you need a sound card, maybe you don't. It will be up to you. But it's definitely worth booking the equipment before Christmas. Okay? I would say it's even worth doing these things as we go. You know, as you're inspired, as you're doing it, just take a microphone back home and do it already. But in any case, some planning ahead is crucial, okay? Just because of the limited gear and potentially because of the limited amount of support you can get, which will be obviously, as I said, 10 days before the submission. Okay, I've got about a month to mark this. In fact, this year, Bruce will help me mark it, so we might be done fairly quickly. Okay, so this is the only one assessment. It is a portfolio of acoustic measurements. This is the word limit. Please don't ask whether it's good to have more or less. You know, that's why it's there. It's not a huge amount of text that I require. So one of the targets is to be concise. Okay, so you don't need to spell out the basic understanding, the basic facts of acoustics at all in this submission. What you really need to do is go in depth on your own work. Okay, those are the learning outcomes. And essentially what we have is 2 out of 4. So I have 4 tasks and you are asked to choose 2 and complete those 2, and that's that. And each one should take 700 to 800 words. Obviously graphs don't count as words, but beware that too many graphs without explanation are counterproductive. Okay, don't assume, and probably you don't anyway, that graphs are self-explanatory. They're not. Okay, so definitely plot a graph, but talk about it. You have to examine it and describe it and produce some conclusions. Now, the recommendation is to put multiple curves in a single graph while it remains readable. Okay? So rather than spending 3-4 pages filling them up with graphs and then having a paragraph on whatever 6-7 graphs, you understand that in observing that, you would have to read the bit, go back, check all 6 graphs. Okay, does that compute? Read again, go back, check the graphs. So your ability to present your understanding in a readable fashion is highly valued. So typically I would say that try to fit it on a single page. Give me a graph with multiple curves or 1 average curve or 2-3 average curves, an informative graph, and then don't exceed the extent of that page in describing it. Because you will see, I mean, obviously it's easy to leave out half a page of text or empty half pages later on or just before, but just to have this impactful page where I see the graph and I can read your description and I can match things very quickly, and you know, you actually find a way to demonstrate your understanding in a really transparent way. All right, so task 1, examine the transmission properties between 3 adjacent spaces. This is the one with the SPL meter. By the way, part of the assessment, and quite a large part of it, is understanding it. Okay, so this has been verified actually for a few years in a row now and externally as sufficient information to understand and perform the task. So if you say, I don't understand it, can you explain it? I will actually shoot a question back at you. Do come forward if you don't understand what's asked for. That's great. But I won't try to simplify it, repeat it, or anything else, but I will try to find which bit are you missing in order to see the picture. Okay? Instead of you know, spelling it out in even more detail, especially because, you know, the way it's created, it's made, the way that I've made it, is that there is always a few really advanced things that you can do that I typically mention in classes that are not part of the instruction, right? And there is typically some very basic mistakes you can make, which are also, obviously it's specified what you need to do, but there is typically, every year I would receive a few of these where people have used a spectral measurement, right? Where it clearly says SPL measurement. Although it's funny because obviously in REW it says SPL. But this is the bit with the SPL meter. Actually, I should probably double check. Does it say SPL meter at any stage? SPL adjacent room. I mean, technically, if you calibrate the microphone with an SPL meter, right, the REW altogether, then you can use this setup as an SPL measurement device. But, it's about the SPL for the whole spectrum. So obviously, people do get confused. Okay, so that's task 1. Task 2, optimize speaker placement in a control room. That's just the title of it. I'll let you read through it and obviously ask questions if you're stuck with anything. Then task 3, specify the suitability of a larger space for music and lecturing. Okay, so this could be one good example, how suitable it is. And we will look at those things. So these first 2 tasks are something that you could already do pretty much based on what we've been through. Task 3, not so much. And then task 4, examine the spectral and distortion characteristic of hardware or software audio processing device. So this will be the interesting thing to realize at the given point, that all the things that we've learned about acoustics and the behavior of sound in spaces is pertinent to linear time invariant systems. And a lot of the audio processing devices are linear time invariant systems. So a lot of these facts hold. And in fact, I will spend a lecture on nonlinearity just to cover the bit that is not necessarily obvious in acoustics. Okay, that's that. There is this bit of, helping you out with the first steps that you might be used to already. Marks and feedback, understanding 40%, right? So I have to assess, the accuracy of the terminology that you command, the completeness, the succinctness, just those bits. Results, so obviously, what seems to be the case in terms of the quality of your measurements, which includes the graphs as well, right? So if you have lovely graphs, which are very informative, you get stuff there. And then presentation, obviously, how it all looks and how it's formatted and all the rest. All right? Any questions? Obviously, I didn't go through all the steps. At one point, you probably will read through, and if there's any questions, I'm happy to help. All right, and then the final bit for today will be me telling you and showing you bits about what is the topic of the second half, which is discovering the characteristic of reverberation. Okay, so first thing, spectral response, estimate the character of reverberation. So what I'm asking you to do is pick 3 microphone locations in 3 radically distinct spots, right? So if this is one spot, I'll probably take it to the corner, somewhere far away, just to get a large, so to speak, difference between the different locations, just so I can see what's happening in different spots in the room. Okay, measurement at each position and discuss the reverberation characteristic. So let's look at this. What are the bits that allow us to look at reverberation itself? I mean, the theoretical background is fairly straightforward to start with, but then there's quite some complexity. Actually, I still didn't link in the videos that are theory-led from previous years. I will do that as well. And you can listen through those if you're really interested. Historically, it was one of the most evasive things. And there's multiple attempts to estimate the reverberation time based on parameters of the room. These are all estimates. In any case, what does the reverberation depend on? Largely depends on size of the room, right? The larger the room, the longer the reverberation. By the way, probably best off starting with saying, how do we measure? What is the measure of reverberation? Standard is RT60, reverberation times 60. And as we progress and look at more acoustical quantities, you will notice that they mostly have an index or a subscript with a number. Because actually RT60, reverberation times 60 dB, tells you the duration, so it's a time, is the duration it takes for the acoustic energy to drop by 60 dB. We also have RT30. We also have RT15. We also have ETD10, which is early time decay for 10 dB. Okay? And actually, if you dig into REW, you will find that there's a few more tricky things that they're talking about, including the Schroeder curve and some more complex stuff that I probably won't get into. But in any case, one thing that I can look at, which tells me something about the time behavior of the system, is the impulse response curve. Okay, it's not hugely informative like that, but this one actually shows a fairly smooth drop. Okay, typically if you look at impulse response curves, if I was probably to set up this against that back wall or get a kind of an arrangement to get to the flutter, you remember in the first class we've identified a fairly strong flutter in this room in a given situation, then what would happen is that I would have peaks recurring, peaks sticking out of the impulse response and recurring at a regular time interval. Okay, so you can actually identify a flutter echo in an impulse response. Now, what are we looking at here? Well, we're looking at dB, and we're looking at time. So I could potentially make an estimate of how long it takes to drop 60 dB. And what becomes the issue here? Well, typically, you would start a bit later. It's a bit tricky. There's a lot of detail in acoustics, including where do you actually start measuring. Mostly it's 5 dB later, so to speak. And I won't go into the explanations. I'm kind of neglecting those things. In fact, I should probably confess that I've also neglected another thing. You probably remember, I think someone even asked, where is the center of the speaker when you were measuring the distance? And I said, well, just where the membrane is, right? But actually, if anyone's interested, I can dig up the paper. People have researched and proposed the acoustic center of the speaker, which is typically few inches in front of the membrane. The way that they've done that is by looking at the polar response and finding the center for the bass frequencies, by the way. And why the hell that is the case, that the acoustical center of the speaker is in front of the membrane? Well, this is the way you can measure it, but if you really want to dig into this, the crucial term is near field. Okay, so in acoustics, there is the concept of near field, which covers the distances very close to the sound source. And as a matter of, simplification, things are weird in the near field. One of the indications that there's something funny going on, I don't know if anyone picked up, but you see, we said that by doubling the distance, we drop 6 dB. You remember this? Which means that by halving the distance, I increase 6 dB. Right? Anyone know Zeno's paradox? So Zeno's paradox says that if Zeno's paradox says that if I walk in this direction, I will never reach the wall. Right? Why is it so that I will never reach the wall? Well, because first I have to come halfway to the wall. then I have to come halfway from the current position to the wall, and then halfway from that position. So it's an infinite series of halvings, which means that I will never get there. Right? So how does this relate to acoustics?
As if you, because you're saying that it increases by 6.
Exactly.
Every time you get closer.
Yeah.
But if you put your ear right next to the speaker,
It's not going to be infinite dB. Exactly. Yeah. So actually, this increment of 6 dB by halving the distance holds until you reach the near field, right? And in the near field, I mean, there is a bit of a poetic description which says something like, well, it takes time for it to shape up. You know, for the sound, because it's actually odd to think that the acoustic center of a speaker is in front of it by a few inches. Okay, so yeah, just a bit of weird details. I hope it excites you, some of you, to actually dig this up. Okay, so that's the impulse response. Now, a group delay, not interested, RT60. Okay, so this is the most pertinent thing here. What we actually see is the reverberation across different frequencies. Okay. Now, if you look at what's down here, what I will suggest, get rid of the optimal curve. And if you want to read about it, go ahead. Early time is also not very interesting. T20 is also not very interesting. T30 is quite interesting. Okay. So I would call the T30 curve the one that we're after. The T60 curve is not being available. Actually, what you have probably, I wanted to say a bit about that, is that one of the problems is that I don't really have a full 60 dB drop before the noise floor, right? So actually measuring the 60 dB, I mean, even if I have extra 10 dB to the noise floor, it's already problematic. So normally when you measure T60, you measure T30 and then you double it, which is a problem, as I will explain in a bit. But in any case, I would call this the reverberation curve of the measurement. And it kind of shows you what you might expect. First thing is that there is much more reverberation in the bass frequencies than in the mids and the highs. Okay, so if you're treating a room, my suggestion is there's many different approaches, people, you know, fighting for their righteous convictions. My humble opinion is that forget about everything, just treat the bass. Because by the time you have enough bass traps in the right places to, you know, get that reverberation down, you will have also tackled the highs a bit, and everything which is not a bass trap will typically decrease the reverberation times, the decay times for high mid frequencies and leave the bass untackled. And actually it is better, again in my opinion, to have a flatter curve than a average lower value, right? Because it's really easy to get rid of high and mids in terms of reflection. So, you know, with a few carpets or, you know, curtains, people like curtains, you know, you will lower the highs and the mids, but the bass just won't be affected. And you get an even larger disbalance in terms of decay times. So I propose that here, the most important thing is the balance rather than the absolute or the average value. Okay, so for a genius idea how I could seemingly lower the bass decay time, I'm willing to offer a pint in the track attack session. Bass traps, obviously, that's the obvious one. No pint for that. The tricky, the uncanny solution, believe it or not, is actually going to be part of today's practical, is plug the port. Okay? So that's this one big elephant in the room. By the way, the Neumann 310s are sealed speakers, yes. and they don't have these issues. Okay, so every, huh?
So for transmission lines, I've got PMCs.
There we go. PMCs, well, yeah, transmission line is much better. Which PMCs do you got?
Oh, only little ones. TB.
There is a pair of LB1s going on for 350 quid, I think, tomorrow on eBay. LB1s are the large ones. If you guys want to buy a pair of amazing speakers for 350 quid, now is the time.
Cheap, I've seen
Where's that?
LB ones with less than £400. It's mad.
That's mad, yeah. Normally it's 800-900 quid for those.
They're not any worse than they were.
They're amazing
because
speakers.
They've made so many new ones.
Yeah. It's just, well, UK Hi-Fi are on eBay.
On eBay?
Yeah. LB1.
There's a pair of I think
Are they Neumanns? or-
No, PMC.
there's a pair in that was in Taunton.
They're passive. Huh?
There was a pair in Taunton on Marketplace for 450 quid.
It's mad. I mean, if you get a catch, you just catch things. It's worth being an eBay addict, I would think.
Building up to is full surrounding second-hand PMCs.
Sometimes you get a deal you don't believe. All right, so plugging the port, because the port is a resonant system introduced in order to give you an impression of louder bass. The matter of fact is that in the 21st century, you have been treated with ported speakers pretty much exclusively, especially if you're not aware of it. Pretty much all the speakers have ports. What happens is you do have a louder bass. It gives you the dopamine rush potentially, but it rings on. Okay, ports ring on. And here you don't quite see it because this is the estimation of what's happening. But if you look at RT60 decay, I'll show you this in a second, but already with this decay curve, what you're supposed to see is how the spectrum develops in time. Okay, so what you see is that where there is a large distance between the top red curve and the bottom blue curve, those are the frequencies that ring out quickly, right? So the blue curve, I don't know if it's obvious what is the time, it's not, but it's probably half a second, something like this. So what you see that within that duration of time, for example, the 10 kilohertz has dropped by 40 dB. But in that amount of time, my 65 dB has hardly dropped. So it's ringing on like crazy, right? So this is something that you should be able to identify. If this is the port resonance, you're using the same design in your practical later on, you should find this exact frequency. And I'm not quite sure, it's probably this one, but it could be this one as well. So it could be a 56, it could be a 69. Okay, remember those two values, see what your measurements give you. And then part of the practical will be to plug the porthole and do the measurement again. Okay, just to see how things develop. Okay, bit more about viewing reverberation characteristic. We have the RT60 decay, which is initially vacant, but if you click the generate button here, then it will compute all of that. And it's a slightly prettier, I would think, plot. And you see it in a bit more 3D, right? So you kind of see that in the bass, everything up until 120 hertz is horrible, ringy, just keeps on happening. What do you get? What you don't get is tight bass, right? You get a floppy bass from this kind of setup. And then actually you kind of see that there is an area up until 400 hertz where things are still quite suspicious in relation to the drop that you see for the rest of the spectrum looking at higher frequencies. So if you want a balanced reverberation in your control room, and I suggest you should want that, you see that's what you're dealing with. That's what you really need to figure out. and the things in the mids and the highs will help, or they will find their way. Now the cool thing about this graph is that as I move the cursor, I see the actual curve that describes the time decay for that specific frequency. So I can go into quite a lot of detail, and in fact I can find the fact, you kind of see it highlighted here as well. So you see that at 92.4 hertz, I've dropped 24 dB, right? And only, at 108, only a few dB higher, I've already dropped a few hertz higher, I dropped already almost 40 dB. So there is this cutoff, you see it on the graph as well. So it actually allows you to examine these things in quite some detail in terms of how the decay curve for each frequency shapes up. Okay, now one thing about these curves, which is a bit of a mystery, like everything in life, I hope, is what does it mean when it dips in relation to when it bulges? Okay, so you will see, for example, here in the low frequencies, here, it kind of starts high, so it kind of bulges to start with, and then it drops. But typically for higher frequencies, you see it drops, and I can find some frequencies where it's even more obvious, then it kind of flattens out afterwards. So there is these two things. Can anyone come up with any explanation why that is? Where could that come from? So the thing to consider is early reflections, late reflections. Okay? So if you have a bulging curve, it means that there's a lot of early reflections, but the late reflections die out quicker, right? If it's the other way around, if it dips immediately, it means that the first reflections are not very prominent, but the late reflections have a decent presence. How could we control that? It's fairly obvious. You probably heard the term treat your first reflections, right? So if you put absorbers where you expect the first reflections to occur, right? And there is supposedly a trick where someone moves a mirror around the room, right? And you look in the mirror, and as soon as you see the speaker in the mirror, it's like, aha, there, right? There are simpler ways of doing this as well. Health and safety hazard, don't move mirrors around the room, who knows. But in any case, those are the two things, right? So if I treat first reflections, I will get a fast drop. If I treat late reflections, which means where am I treating? Typically corners, right? So if you imagine, where you're sitting now and all the paths from this speaker to you, the first order reflections would be, ceiling, floor, this wall, that wall. Second order reflections would be a bit of back and forth. So ceiling, floor, then you. One wall, second wall, then you. So actually all of these locations in terms of reflection will be somewhere in the middle of these walls. It takes a higher order reflection to come into the corner, right? So if you put absorption in the corners, then you are more treating late reflections. I mean, there is something to say about energy buildup in the corners, and actually, on top of that, you will be, tackling that. But what we're discussing here is this curvature characteristic. So why is it that in the bass, I get the bulging thing, and in the high frequencies, I get this dipping thing? Yeah, it's that simple. Yeah? The bass stays in the room, right? Especially if you have concrete or brick walls, the bass stays in the room. Okay, it stays on. Cool. I think I should wrap it up. Are there any questions in the meanwhile? Okay, so those are the ways. I think I've been through most of this. RT60 decay. There is this decay plot that I've shown you. It's also quite neat. And there is the waterfall plot as well, which also shows you, those are the ringing frequencies. You see some anomalies here. You can probably identify one or two proper rings. But the real interesting thing to observe is you see that actually, in terms of reverberation, we have a dip in the middle, right? So these frequencies decay much faster. We seem to have quite some high frequency reflection in this room. All right, that's about it. So task 1, reverberation characteristics with wild positions in the room. Task 2, did I say tax? Task 2 is plugging, sorry, what am I saying? Oh no, sorry, this is the last week's. So task 1 is radically different positions. Task 2 is plugging the port versus not plugging it. And then, if you're still around and working on it, absorber, whatever, there are absorption panels with the technicians. So if you're still, full of stamina, but it's sunny evening, we'll see, grab one of those and compare measurements, compare the absorption characteristic when you put it behind the microphone and when it's not there. Okay? Just to give you a sense of how much of the reverberation this could, remove, which is obviously pertinent to recording. If you have a room that you don't want to capture the sound of, just to have an idea, if I do this, is it worth doing, so to speak? Okay, so this week all the kits are in the technician's room, so just go and grab one, take it to the studio that you desire to work in. Try not to make huge groups, but I'll come around and help you with that. All good? Cool, thanks for coming.